Hi students, I wanted to start you today with this warm-up problem as you see that I present, and before you go blasting on past this portion of the video, I wanted to tell you that this closely mirrors a test question. So please take a close look at this, and you'll notice I give you 6 different elements, but only 5 different inequalities that tell you A is less than E, F is less than B. So if this is some linearly ordered set, give me all the possible orderings on this set. I'll give you the hint that there's actually 8 different possible correct orderings for this that satisfy the 5 inequalities you see here. So again, I would ask you to pause this video. Don't scroll down yet. Just try sketching this out on a piece of paper. And once you've tried that, now we'll scroll down and take a look at the key. All right, so go ahead and pause right now, and I'll see you on the other side. Okay, so great. Is this what you came up with? As you can see, there's your key. Good. A couple of topics today: linearly ordered abelian groups. When we were talking about we talked about linearly ordered groups before, but yeah, whenever you have an ordered abelian group like this, quite simply put, yeah, S star forms an abelian group, but also you can order the set. You have a linearly ordered set, and you have monotonicity. And importantly, because of the presence of commutativity on such abelian groups, I promise you such an ordered group will have extended monotonicity. And you may recall what extended monotonicity was. That was where we had if A is less than B and C is less than D, then A plus C was less than B plus D. That has to be the case. Of course, also, obviously, the converse relation, in this case greater than, would also be, that will also work. That'll be an ordered group as well. So anyway, when you get to exercise 36, I give you a hint here on this one. I tell you, hey, the answer is not yes. I want you to consider a component-wise operational system on Q cross Q with component-wise addition, and then of course component-wise less than. And this is how we define this system, where we say the ordered pair A comma B is less than C comma D, A has to be less than C, and B has to be less than D. Now we'll have some other kinds of orderings later on, but so this is rather important on this one. When I say, is this an ordered group? Again, the answer isn't yes. Okay, so talk with your classmates about this one, about what do you suppose what is the reason that you're going to mark no. There's 4 different ways you could say no, and put in the correct counterexample, please. All right. So there's a video about talking about some of these ordered groups. I'll have you take a look at that one on your own as well. We talked last week for a bit about first elements and last elements is defined as such. I had you write your own definition for last element, as you may recall. So as we scooch on down here with some of these exercises, you're going to find that some of these exercises are probably best suited for me to either load a model answer or just talk you through them. I'll talk you through a few of these for right now, where we've got this statement where the first element is S, last element is T. If we suppose further that S equals T is what we're looking for here on this little explanation where they're going with this. Since A has at least 2 elements, it follows there has to be some element of X such that X is not S and it's not T either. And it would follow that X is going to be some element of A minus that element S. So since S is the first element of the relation, we'd say S relates X like so. And similarly, if if T was the last element, then we'd say X relates T like so. And from transitivity, we would conclude S relates to T, but R has trichotomy over A, and we cannot have it that both of these S equals T and S relates to T is true. So therefore, we've proven that by negation that S cannot be T in exercise 38. So the extreme elements theorem is also part of this section here. If we have a finite set of elements in A and it's described by n, then all relations R on a linearly ordered set must have some first and last element, no matter what. And so first section of to prove this by induction, if we assume A had, say, 2 elements and R is a linear order on A, if I had number of elements and A was 2, there must exist 2 elements that aren't the same, such that A is not equivalent to B, and A is going to be composed of the set of AB. So since A is not equal to B, it follows that either A relates to B or B relates to A, but not both. So let's consider case 1, where A relates to B. We have that for all x's that are elements of A other than little a, we would be able to say that A relates to X. That would tell me that A is the first element. Similarly, we would also be able to say that X relates to B like that. So that would give us B as the last element. Now case 2, we'll flip this around where B relates to A like so. We would say that for all elements of X, B relates to X like so. And similarly, to show that A is last element, we'd say X must relate to A like so. In either case, we definitely have a first and last element, and that establishes our base of induction. So, and as you can see now, exercise 40, it definitely, this one gets a little bit longer insofar as the proof goes. And I'll just go ahead and fill you in on this with respect to how this is going to work. This again, we're just talking about, hey, so if you have this element E that you don't know anything about, maybe it's the first element, maybe it's somewhere in the middle, or maybe it's the last element, and that's why they have these proofs by 3 cases. But we'll just fill this in with S relates to X, and because of transitivity, we know that E relates to X. In either case, we know E relates to X like so, and E, that would tell us that E is the first element of the set. If Y, if I've got some element Y that's not E, it's either, or excuse me, Y is either E or it's not E. If I assume that Y equals E, then we'd have Y relates to S. Since B has at least 2 elements, as we said right here, that S is not T. Since T is the last element, I'll write S relates to T for set 1 relation B. So I'll say S relates to T like so, and by transitivity we would conclude Y relates to T like so. And that's going to also fill in down here. In either case, we're showing Y relates to T, and this would show us that T is going to be the last element of AR. All right, so I'll go ahead and load in these model answers for the next exercises that goes all the way through 44. It's a decent discussion that could span a couple classes if I allowed it, but time's running short. I just want you to go ahead and complete through exercise 44 on page 28. And again, like I said, exercises 41 through 44, I'll just, starting from this point on down, I'll just load the model answers for those, and you'll just make you responsible for the rest. Make sure you study that example, of course, that I also provided in the warm-up questions. Make a note on that, and make sure you're studying it. All right, thank you for listening here today. Be sure to subscribe to my YouTube channel, and I will see you soon. Bye-bye.